A CNC mill in a home shop is often a set of compromises that are optimized to a price point. We only have so much money to spend. We're only going to get one machine, but we want to process a variety of materials: wood, plastic, aluminum, steel, stainless steel. That means that we're going to be limited by something when we process any of those materials. And most commonly it'll be spindle speed, spindle torque, or feed rates will be limiting factors. I've wanted to experiment with a secondary spindle, that is, mount a second spindle on the side of the mill's head. And what's really great about that is that you get to reuse all the motion control hardware and software that you have on the CNC mill. A lot of people use trim routers, but I really feel like the trim router would have a long life to it if you're running it for hours on end. I had this spindle. That's a 2.2 kilowatt, 24,000 RPM spindle. And the main spindle is 5,500 maximum speed, is 750 watts. And you say, well, that's a huge difference in power. But remember, as you go to higher speeds, more of that power is going to be used just to maintain the speed. So it's not quite as big of a difference as it seems. One thing I'm going to use this spindle for right away, as kind of accelerated getting this done, is isolation milling a PCB. The rest of the video will talk about how I mounted the spindle, made the plates to mount the spindle, the software changes that are necessary to do cooperation between the two spindles, the measurements that are necessary, and finally some test parts. So hope you enjoy the video. Thank you. I used two plates to mount the high-speed spindle, and the idea is that the lower plate against the head could be a flat reference surface for another tool. If you think of the high-speed spindle as just a generic tool that gets mounted onto that plate. I don't have other tools in mind right now, but I have mounted other things onto the side of the mill's head before, cameras and sensors. So there's some history of using the side of the mill for mounting other devices. I spent time flattening the two large faces of these plates so that there'll be a lot of surface contact between them. I used sandpaper and surface plate to do that. Before this video, the main spindle has already been trimmed, but the mill's head is a casting and it's not very flat or square with respect to the spindle. So to get this plate so that it's aligned with the spindle in one dimension, I'm inserting shims, and then it'll be square to the table. You know, the main spindle's been trimmed, so it's square to the table and in two dimensions. And now I'm aligning this plate so that it's square to the table in one dimension. Because we're aligning two rotary devices, there's no need to align this plate or square this plate in this case in the Y direction. The power cable I'm using for the high-speed spindle is a VFD cable from Automation Direct, and has a high voltage rating, so it has a thick insulation. It's a fat cable, but it's also shielded and it should cut down the noise from the VFD. I'm using almost a 12-inch rod for tramming the high-speed spindle. It's pretty true in the X direction already. And only a little bit of adjustment was necessary in the Y direction. So spending time to get that lower plate squared was time well spent. This is an ER20 spindle, and I'm measuring the runout on the collet mating surface. There's practically no measurable runout on this surface. I'm limited much more by the flex of the mill than I am by any runout on the spindle. Granted, I'm measuring the flex of the head at its extreme vertical position, so it's going to be exaggerated there. Tool runout was less encouraging with about 1,000 total runout. The short answer why I saw the 1,000ths run out on the tool is I hadn't torqued the ER20 nut sufficiently, and the quality of the collet itself. That collet came from this set. It's a set of 30 from Tormach, and this set costs about $200. This single collet came from Linux, and I bought this from McMaster, so there's a McMaster premium to be sure. It's about $41. That's about 6 times the cost of the Lindex collet versus a single collet out of that set of 30. To torque it, I use a torque wrench with a head that can be replaced for an ER16, ER20, ER32 collet. And I got that originally for torquing TTS tool holders. Now, what I started with the TTS holders were these aluminum wrenches, and they are aluminum because you can tell because they will round out if you try to tighten things too much. But they work well. I still use these a lot. But they're hard to hold and torque consistently. So then I got this holder for TTS tools. You slide the TTS tool holder in here. It's a one-way roller bearing, and one way you can tighten the nut, the other way you can loosen the nut. But when you start torquing the TTS holder to 58 foot-pounds, it starts to slip in that one-way roller bearing, so that's not great either. So these tools kind of sat unused until I got the high-speed spindle. And I started first installing tools into the high-speed spindle using adjustable wrenches. So one set to about 17 millimeters and the other one set to about 30 millimeters, and you just slip them on and tighten them. And that worked terribly because you need a third and a fourth hand to hold the tool. The tool drops, the carbide tool drops onto a cast iron surface. It's done. And these wrenches, these don't work. The ER20 part, this works fine. But if you have larger tools, you can't slide this over. And this part is too large. So what I came up with, and I'm hoping that someone watches this will have a better suggestion, but a 21 millimeter wrench with a hook on the end. To loosen a tool, I install this and hook the wire around a screw in the back and use an excessively large breaker bar with a 30 millimeter adapter on the end. This is what I had for a breaker bar that's reasonable length. Well, yeah, reasonable length, and the rest of the way you can loosen it by hand. And then to tighten it, I rest the wrench on the fog buster and take the torque wrench and be sure that you're torquing in the right direction. Otherwise, it will, you over tighten the nut for sure. Just tighten until it clicks, and it's done. 58 foot-pounds. I'll take this off. So I'm going to put the 3/16" tool back in and measure runout again, just as demonstration. But this is how I solved that bit of runout. But like I showed in the video, you can press on the side of the head and create far more deflection than the runout was producing. So, okay. I want to be able to use the two spindles cooperatively, so within the same program, switch between them, taking advantage of each of their better features. To do that, I need to know the offset between the center points of each spindle. I'm using a Drutronics touch probe to measure the machine coordinates of a reference point, and when this is done in each spindle, the difference between those coordinates will be the offset necessary to move between each spindle. The X and Y offset can be preloaded in a G92 offset, and then that makes it really easy to update these values but keep the program the same. Even within the cam setup, it's not necessary to explicitly select one of the spindles. Tool length is always measured relative to the nose of the main spindle, regardless if the tool is mounted in the high-speed spindle or in the main spindle. And this is hugely simplified by using the tool length probe. The spindle speed is controlled by an analog input from a Mesa 7976E card into a VFD. And out of the box, the commanded to actual velocity agreement was pretty good, except on the low side. I tried a couple of different ways to improve that using a PID control loop, which is what I'm demonstrating here. And it's really neat about LinuxCNC. You can update the values of the PID control loop and see the effect on a oscilloscope-like interface. In the end, I use a simpler piecewise linear function using the lin curve Hall component. And again, you can tinker with the values in LinuxCNC and verify them without having to restart LinuxCNC, and that's really nice. I also wrote a Python module to retrieve the parameters from the VFD to create a backup of them, to set parameters and to read status conditions. That's how I get torque and voltage measurements from the VFD. I would probably use a Python module for speed control for redoing this work. There's a dedicated fault line from the VFD into the Mesa board, so it should be pretty safe even if there is a fault in the USB to RS-45 converter. To test the cooperation between the two spindles, I started by cutting parts in wood, and it's really neat to see the division of work between the two spindles in the projection of the G-code in LinuxCNC. Tool 150 is a tool mounted in the high-speed spindle, and on the right-hand side of the screen I'm showing the status from each spindle, including speed and torque measurements. To automatically switch between the two spindles, I modified the LinuxCNC post-processor that's used by Fusion360. The left-hand side of the screen contains both my changes and updates from Autodesk, but I'll point out the changes that I made. I keep track of the currently running spindle and calculate the new spindle based on the requested spindle speed. The main spindle can't operate faster than about 5,500 to 6,000 RPM, and the high-speed spindle can't operate slower than 9,000. If the calculated spindle is different from the current spindle, then I know a spindle change is taking place. I warn the operator that a spindle change is occurring. LinuxCNC 2.8 and above add $ arguments to the M3, M4, M5 commands, and they route the command to the appropriate spindle. So if the new spindle is the main spindle, I write a message to the LinuxCNC screen saying that change to the main spindle is in progress. I disable or stop the high-speed spindle, so that's the second spindle, or $1, so M5 $1, and disable and save the G92 offset. If the new spindle is a high-speed spindle, so the current spindle is the main spindle, I stop the main spindle, so M5 $0, and restore the G92 offset, so G92.3. Then when the spindle is started, I need to send the appropriate M3 or M4 command, depending upon direction of rotation, and then the $0 or 1. If the speed is changed, so if you're using the same tool and the speed's changed, then a little bit of code update is needed to handle that. This probably has a mistake in it, right? Let's say operating on the main spindle and the tool doesn't change, but the requested speed increases beyond 6,000 RPM. This is going to activate the high-speed spindle. So this might have a flaw in it, that it also needs to check which spindle is currently running. And then finally, to handle the stop spindle command, I stop all spindles. Now the same part will be machined in aluminum, and with the exception of the main roughing operation, which is only done by the main spindle, all operations are performed by both spindles to help compare them. Don't really feel any ridges in the wrong direction, but pretty rough in the X direction. 3/8 inch 3-flute end mill, 24,000 RPM, 170 inches a minute, 2,400 surface feet per minute. On one pass, like this very first one, it looks great, and then coming back the other direction, it looks poor. So it looks great here, in the first pass, and then poor, great, cool, great, it alternates. Yeah, it's great, it's really smooth. I think there's a lot of potential there. Just need to improve the settings. This is the main roughing operation using a 3/8 inch roughing end mill. It's a highly serrated, really wicked looking end mill, 5,000 RPM. The only reason I only ran this operation on the main spindle is I only have one of these end mills. Unfortunately, when I made this video, I also only had one 3/8 inch finishing end mill, which is mounted in the main spindle in a tool holder. The high-speed spindle has this finishing roughing end mill, and we'll see a problem with that later. This crash, like all crashes, was really interesting. There's something to learn from this. If you watch the status indicators in LinuxCNC, right before the crash, the torque spikes up, and the spindle indicates a fault, and then the axes fault, and then finally LinuxCNC faults. I have separate fault indicators for the axes as a group, the main spindle and the high-speed spindle, and they OR together into a single fault indicator in LinuxCNC that shuts the machine down. Unfortunately, I hadn't propagated all of the second spindle updates through the code. Replaying the operations up to the fault at 200% override, and then drop back the feed rate to 70%. This is a 3/8 inch end mill, and only had one of these, otherwise there would be another in the high-speed spindle. The end mill in the high-speed spindle is similar in appearance, except it has notches along the flutes, maybe 3 or 4 notches per flute. It's a finishing roughing end mill. It's supposed to leave a smooth finish, but instead it leaves ridges at each of those notches. So I don't use those end mills anymore. The floor isn't too bad, but the walls have this texture on them. And I always see that texture on this mill. Some speeds are worse than others. It's not great. Doesn't take very much to sand it off, but it'd be nice to not have to do that step. Essentially, each spindle is performing the same finishing operations. The roughing operation left 40 thousandths of an inch axially and radially, and each finishing operation performed by each spindle is taking off 20 thousandths of an inch of that leftover material. You have those rainbow interference patterns you get with carbide insert tools and wipers, and I don't feel really any roughness, destruction. The walls look really good as well. You can see a good reflection, and I don't feel any roughness moving this way. There are ridges moving this way, 2 or 3 ridges, and that's because this is a finishing roughing end mill. It has chip breakers, and just end up leaving these ridges, so I don't use them anymore. Inside, this is where it was running faster. It was 168 inches a minute, but it's 2,300 surface feet a minute, so beyond the 2,000 recommended. I slowed down the feed to 70%, and you can see we went from this kind of rough pattern, which isn't really that bad to feel, to this, right? I mean, you can see the friction there. It's definitely distorted there. I'm repeating a couple of the high-speed spindle operations using a slower feed rate to see if doing so will improve the surface finish. Came back and redid the inner surface, this inner wall, and this top face at 70% of 168 inches a minute. Slowed it down a little bit, and that's what these walls we're doing that. And it's drastically better. It's just going to take some experimenting to get the speeds and feeds right. You can do a really great job. Now, this is only the first part of cut with this spindle. Aluminum, really amazing.